Hello students, so continuing our lectures on surface tension, we will discuss about shape of large liquid drops. In this lecture, we'll start with this one. Now, whenever you have a liquid drop on a surface, usually if it is small, it usually takes the shape of a sphere, as we have found in our previous class. It takes a spherical shape. However, if you increase the size of the drop, and you may find that it actually starts to wet the surface. That means by wetting, that means it grows horizontally. So it is when it is large enough, then the upper surface is sort of a horizontal, like as you find in this case, it is losing its property, it is deviating from the shape of a sphere, and the diameter also is large enough to its thickness. So this is how it would look like. Now if we put the angle phi, angle theta, this is the contact angle psi, and this angle will be represented by theta, then the pressure inside the water droplet, as we have found in our previous cases while blowing a balloon, we have found that the pressure is 2s, sorry, pressure we have found is 2s by r, the pressure outside the balloon surface. So with the same notion, what we can say in this case is the pressure is, inside pressure is P is equal to S divided by 1 by R plus 1 by capital R, the radius of curvature. So this pressure is being acted upon, and another pressure which is called the external pressure. Now y square has been found to be equal to 2b square minus cos psi. If this is the case, then ultimately what is obtained here is g rho y square by 2 is equal to S1 minus cos psi, where b square is equal to S by rho g, S by rho g. So this is how the equation look like, and at the point where so as the size of the drop increases, this angle starts to go down, and there is a time where this angle it tries to it increases and it reaches 90 degrees at a certain time, okay, as the group is growing. So in this case it might be like this. It is initially like this. So as it grows in shape, there is a time when it actually is like this. So this is 90 degrees. So what we can write here, at the point where the drop becomes vertical, this region becomes vertical, then psi is equal to 90 degrees. So cos of psi is equal to 0. So the previous equation now S is equal to G rho y square by 2. By y we mean this value, the growth of the drop in the vertical direction. Okay, and if it grows in the horizontal direction, then there will be a point where psi will be equal to 90 degrees. Sorry, psi will be equal to 0 degrees. So in that case, your cos theta, we can now represent the psi not in terms of psi but in terms of this angle theta. So in that case, the height will be equal to the total height h from the center of gravity, or rather it is called it's not the height from the center of gravity but the thickness of the drop. So center of gravity, height from the center of gravity will equal to the thickness of the drop, and we will ultimately achieve the equation as rho g h square by 2 is equal to s1 minus cos theta. Okay, so the next topic is rise of a liquid in a capillary tube. Now, there are basically two cases when we are considering, in fact, three cases. The first one is when we are considering the tube to be very narrow. If the tube is narrow enough, we can assume that the liquid is in spherical shape and the contact angle is 0. If that is the case, then simply the equation will be 2s by r is equal to rho gh, or this is the equation. This is how the equation will be, and so we can find out the value of s from this region. However, if the drop is not small, or rather the tube is wide enough, okay, then we need to have a certain positive value of contact angle, which is theta in this case, and based upon this theta, what we can say is that this r, radius of curvature, and will have a relationship with r, that is r cos theta will be equal to r. So our equation will simply turn out to be rho gh will be equal to, instead of 2s, it will be 2s by r with a cos theta multiplied. This is how the equation will look like. And the third case is when we are assuming the cylinder to be perfectly cylindrical. In that case, the shape is actually, it takes the shape of an ellipse. An ellipse. Okay. Now the ellipse again, in this case, the radius of curvature r will be equal to r square by B. Okay, so this is R square, this is R, and this is B. So radius of curvature will look like this, considering it to be an ellipse. This is R and this is B. Now what we do here, we equate the resultant force, that is 2 pi Rs. This is the resultant force which is acting in upward along the circumference of a circle of radius r to the weight of the liquid raised. So we are equating the resultant force which is acting upward along the circumference of the circle. That is, we are basically talking about the force due to surface tension, and we are equating it to the weight of the liquid raised. So again, weight of the liquid raised can be expressed at pi r square, the area, multiplied by rho gh plus 1/3 pi r square, considering the cylindrical shape of the tube, into B rho g. So in one case we are considering the height of the liquid, in another case we are considering the value B. Okay. Now in this particular case, as we have taken a constant B in the previous cases, similar to that we can also associate a constant S by rho g as equal to a square, and since we have previously said that R is equal to, capital R is equal to R square by B, we can say that 2a square is equal to RH. Because 2a square means we are talking about 2s by rho g. This is equal to a square, this is equal to 2a square, and 2a square by rho g is equal to RH. So that's why S by rho g, this is equal to RH. So that is why 2a square will be equal to RH, and R by H tends to 0 as the liquid increases in size, and so we can write this S by rho g, which is equal to a square. You can write it is equal to 1 by two RH into a series R plus 1/3 R by H minus 1 by 9 R cube by H cube. So taking only the first approximation, what we finally obtain is S is equal to RH into rho g divided by 2. Now for a given liquid having a particular value of surface tension and density, what we can say is that RH is usually a constant. So this is known by a law. This is called the Jurin's law. Okay. The next case is the rise of a liquid between parallel vertical plates. So we assume that again it is a cylindrical shape. This section is cylindrical shape, and if it is in cylindrical shape with diameter d, and the pressure at this point, pressure occurring at this point, which we are considered it to be V, is less than the normal atmospheric pressure by S by R, and which is again equal to 2S by D, where D is equal to nothing but twice of R radius, and H, if H is the rise that has occurred due to this contact angle, then it's simply 2S by D is equal to rho G H. This is what happens in the case of liquid between parallel vertical plates. Now, another aspect to the surface tension is the saturated vapor pressure over the curved liquid surface, and it has been found that the saturated liquid pressure of, we're calling it as SVP of the convex is usually greater than the SVP of the concave. When it is in plane. Okay. Oh, rather it's not. These. So plane is in between them, and okay. So the convex has got the highest vapor pressure, and the concave one has got the lower pressure. And the equation which relates the different pressure, the plane pressure with the surface pressure, is this one, is given as log capital small p by capital P is equal to 2S by P R T. So this capital P is the surface saturated vapor pressure, and the small p is the equilibrium pressure over a curved surface of radius r. Now there are certain conditions which are valid here. The conditions are that for a given pressure P, that is for a given degree of supersaturation, if this value, this radius of the curved surface is less than the radius of curvature, then it will evaporate. However, if the radius of the curved surface is more than the radius of the curvature, then it will grow. Okay. Now this above situation has also is also applicable in the case of boiling of liquids. As you can see, the above idea also holds in case of boiling, as a pure liquid may be raised to a temperature much in excess of its normal boiling point, and if it is free from the impurities which provide nuclei for the bubbles of the vapor to form. You can see here. Next is when the formation occurs, the growth of the bubbles is however very rapid, and since the surface tension is increasing but insufficient to counteract the excess pressure inside, in this case boiling of the bumping occurs. That means the boiling point shoots up a little bit. And while in the case of normal process of boiling, the bubble contains some gases as well as the vapor, and in equilibrium, when the pressure P2 due to the gases equals the necessary excess pressure inside over that outside the bubble, then what we can see that if we have two different pressures, one is the P1 pressure, which is the external pressure, and there is another pressure P2, which is the vapor pressure inside the bubble formation, then P1 and P2 will be again equal to the P. The P is the equilibrium pressure plus 4S by R. 4S by R, because here again there is not only one medium but there are two mediums. So instead of 2S by R, we will be writing here 4S by R.